Hi friends, today we are going to start lecture 25 on our helicopter dynamics course. Today I am going to discuss the Rayleigh-Ritz method. I am Dr. Ranjan Ganguly. Now we saw in the last lecture in the Galerkin method that this method was based on the governing differential equation for the problem. In contrast, the Rayleigh-Ritz method is based on energy principles. So essentially here we are going to take the kinetic energy, potential energy and virtual work in the system, and we are going to use these to derive the natural frequency of a rotating beam. So one of the aspects of these methods is similar, which is that you have to assume the deflection as a series of functions, and these are the basis functions. And in the Rayleigh-Ritz method, it is sufficient that these functions satisfy only the geometric boundary conditions, that is, the deflection and slope are zero at the root for a cantilever beam. Now there's nothing wrong if they satisfy the force boundary condition. That will give you a better result actually, but it's not necessary here. So again, remember the problem we are dealing with. We have a cantilever beam. It's rotating with a rotation speed. We have a forcing on this beam Fz Rt, and the displacement is given by W, and we are using R for the spatial coordinate along the blade. So the starting point of all these approximate methods is to assume the deflection of the beam or blade is given as a series solution. And here we take a n-term solution, so I is 1 to n. And we take these functions of R, these are the basis functions, which essentially represent the shapes in which the beam can deflect. And the next part is the function of time, which become the degree of freedom for this problem. So essentially what you are doing here is you are approximating a continuous system by a limited term solution and a discrete system. So essentially we will reduce the infinite degree of freedom continuous beam into a finite degree of freedom discrete system. So now, like I mentioned, for the cantilever beam, the geometric boundary conditions are given here. At R is 0, W and W dash are 0, which of course would mean that Y at 0 should be 0 and Y dash at 0 is 0. So in the Rayleigh-Ritz methods, it is more easy to find the basis functions which satisfy these geometric boundary conditions, because we saw in Galerkin method to find the function which actually satisfied the force boundary condition is somewhat more difficult. Of course, you can use beam functions which satisfy all the boundary conditions in any of these problems, but sometimes beam functions may be difficult to perform integrations on unless you are using Mathematica or some solver like that. So now we start with the kinetic energy of this system. So we take a small mass m into dr, and we calculate the kinetic energy of this mass. So that would be half of m dr into w dot square. So w dot is going to be the velocity of this small mass, and then we integrate this entire ke of this mass across the entire domain here, and the domain is the beam, so you integrate from 0 to r, and we can refer to this kinetic energy by ke, or sometimes we also call it t. So now what we do is we discretize the ke, so we take the expression for the ke and we put our series solution into this equation. So here you can clearly see I can differentiate w here, and after differentiating here I plug these in. So on one of these I put subscript I, and on second of these I put subscript j, and then I can write this in a summation form or a double summation form, provided I use this notation here, that is mij is integral 0 r m yi yj dr. So essentially the mass matrix is going to be represented by the mass and by the basis functions we have selected for this problem. Now we continue this process and get the potential or strain energy for the problem, so sometime called PE, and the strain energy is sometimes referred to as V. And the strain energy has two components. The first part is due to the flexure, which some of you may be familiar with from your mechanics of material. Now, this is the part which comes from the stiffness of the system. So essentially, because there is a stiffness in the system, some energy is stored here. Now, the second part is coming from the centrifugal stiffening. So this is a very general expression. Whether you have a blade which is having T is constant, that means it's a stiff string, or it has a rotation speed where T is a function of X. Essentially, the effect of tensile forces is to stiffen the blade, and therefore this shows up as a positive term as far as the potential energy is concerned. Now, many people mistake that the centrifugal force and the tensile force all should impact the Ke, but actually if you see, it impacts the Pe here. So again, we perform the same mathematical jugglery. We take our W series expansion and we substitute it in V. And once we do it, we get this complicated equation here, which can be simplified provided you recognize that these are essentially coefficients of Qi and Qj. And so if you recognize that, you can lump all the remaining terms into one term Kij, and you can write it in a nice compact form, which essentially becomes the stiffness matrix of the system. So here also you are discretizing the system. You are taking an infinite degree of freedom system and converting it into an n degree of freedom system. Okay. So now once you do that, this is the form of the stiffness matrix. So stiffness matrix tells you the same thing, that there is a stiffening effect due to the flexural stiffness, and there is a stiffening effect due to the tensile force here. And remember that T itself is a function of R given in this manner. So this formulation can actually handle any kind of non-uniform beam also. So again, it's not just limited to rotating beams. Even if you have a problem where EI is a function of X or M is a function of X, you can use the Rayleigh-Ritz and Galerkin method, which we discussed in the last lecture and we are discussing in this lecture. That's the point to keep in mind, that these methods are quite ubiquitous as far as mechanics is concerned. Now, the third aspect we can consider is the virtual work done due to virtual displacement. And again, the work done is going to be the force into the displacement, and here the displacement is virtual. So remember, this force is the fluid mechanics force which acts on that particular section dr. So we can again write this in a simplified form here, provided we create a load vector qi. Now what we do with this t, v and q is that we put all this stuff into the Lagrange equations, and the Lagrange equations essentially minimize the energy in the system and give you the path which the system is going to finally take, the equilibrium position. And by doing that, we obtain a simple matrix equation of size n. So again, you have now n degrees of freedom, n being this capital N here. You have the stiffness and mass matrices and the load vector. Now today we are interested in basically getting the frequency. So we'll use the Rayleigh-Ritz method here, and I will use a one-term solution. So the one-term solution is given here. That means I'm retaining only n equals 1. Now I get this equation here, and so the solution of this problem is given by the stiffness by mass, K11 by M11. So essentially this is K11, this is M11. So now to calculate this, I need only to know EI, T, M, and I need to use the assumed basis function. So of course you realize that all these methods are very dependent on the choice of the assumed basis function y1. So we take a very simple function for y1, because remember Rayleigh-Ritz method this needs to only satisfy the geometric boundary conditions. So this clearly satisfies the fact that y1 is 0 at r is 0 and y1 dash is 0 at r is 0. So I can immediately get the mass and stiffness matrix terms. So this is simply a one-term solution. So these are one by one matrices. So I get these two here and I can immediately form my frequency for the problem. So dimensionally this of course looks okay. There is a EI by MR4 here, which we saw in the non-rotating beam type of situation, and there is a stiffening effect due to the rotation. So you will see that this particular solution we have obtained here is not going to be as good as the Galerkin one, because the Galerkin one had somewhat better basis functions. But if you use the basis functions we used in the Galerkin one, which satisfies all the boundary conditions, you are going to get a good solution for this problem. So that ends lecture 25 here. I will see you in my next video.